Lesson 99, Volume Ratios of Similar Solids. In this lesson, students explore the relationships between the surface areas, volumes, and perimeters of corresponding faces of similar solids. The warm-up, number 1, a polyhedron with a rectangular base and 4 triangular faces that meet at a vertex is called a rectangular pyramid. Determine the volume of this solid. The volume of a pyramid is 1/3 area of the base times the height. Make sure you write a capital B, which is area of the base. The base of this figure is a square, 3.5 by 3.5. So the area is length times width, or 3.5 squared. The height is 2.7, and we take 1/3 of that. The 3 will cancel with the 2.7 and leave 0.9, and so you have 3.5 squared times 0.9, which is 11.025 cubic centimeters. Number 3, what is the height of this solid? They have several numbers listed and they want you to figure out which one is the height. This is the height from the vertex to the plane containing the base. So that height is 3.9, which is B. Theorem 87.1 gives the relationship between similar polygons with sides that are in an A to B ratio. Theorem 99.1 provides a similar rule for three-dimensional solids. If two similar solids have a scale factor of A to B, then the ratio of the perimeters of their corresponding faces will be the same, A to B. The ratio of the areas of their corresponding faces is A squared to B squared, and the ratio of their volumes is A cubed to B cubed. Example 1, corresponding perimeters of similar solids. Two similar rectangular pyramids have a scale factor of 3 to 2. Determine the perimeter of the smaller pyramid's base. The larger pyramid's perimeter is 2 times 3 plus 2 times 7.5. So we get 6 plus 15, which is 21. The scale factor between their sides, between the two pyramids, is 3 to 2. 3 to 2. The larger one, 3, 2. We know the perimeter of the larger one is 21. So if the scale factor is 3 to 2, then their perimeters would be 21 to whatever the perimeter of the smaller base is. So when we cross multiply, we get 3x equals 2 times 21 and divide both sides by 3. We get x is equal to 14 inches. Example 2, finding surface areas of similar solids. The surface area of the smaller pyramid is 54 square centimeters. The smaller one, surface area, is 54 square centimeters. What is the surface area of the larger one? And they give us the scale factor is 15 to 6. Now that's the scale factor of their sides. Reduce that and you get, both of them will divide by 3, 5 to 2. Now that's the scale factor of their sides and their perimeters. So remember, the scale factor of their sides is A to B. The scale factor of their areas will equal A squared to B squared. So the scale factor of these areas would be 25 to 4. We do not know the surface area of the larger one. We know the surface area of the smaller one. Cross multiply, 4x equals 25 times 54, and divide both sides by 4. 337.5 square centimeters. Now remember, if the ratio of their sides is A to B, the ratio of their areas is A squared to B squared. Example 3, finding volumes of similar solids. The two solids shown are similar. If the volume of the smaller cylinder is 38 cubic feet, what is the volume of the larger cylinder? We know the ratio of their radii is 3 to 2. The ratio of their volumes would be 3 cubed to 2 cubed. So when we go to set up our proportion, 3 cubed is 27, 2 cubed is 8. So we're going to set it up 27 is to 8, as we do not know the larger one. We know the smaller one is 38. And 27 times 38 divided by 8 will give you 128 and 25 hundredths cubic feet. B part, prove the third part of Theorem 99.1 for a pair of similar pyramids. We have two pyramids. We'll call one of them K and one of them L. We know their sides, their heights are going to be in a ratio of H sub K to H sub L. We know the area of their bases are B sub K and B sub L. So let's use the formula for volume of a pyramid, which is 1/3 area of the base times the height. So we have to find the volume of pyramid K would be 1/3 area of the base of K times the height of K. If these are similar pyramids, then we know their sides, their heights, their linear measurements are in a ratio of A to B. Therefore, if we substitute for the height, we know that the H sub K is going to be A over B times H sub L. They have that ratio of A over B. Likewise, their areas are going to be in a ratio of A squared to B squared. So the area of, we can substitute the base area of the other pyramid for A squared over B squared, B sub L. When we simplify this, we get the volume of pyramid K is A squared times A is A cubed, and A B squared times B is B cubed, times 1/3 B sub L H sub L. Therefore, we know that the volume of one of those pyramids has a ratio of A cubed to B cubed for the volume of the other pyramid, which is 1/3 B sub L H sub L. Example 4, application space exploration. A proposed crew capsule for space exploration is shaped like a square pyramid. A scale model of the capsule has base sides of 26 inches each and a height of 15 inches. Determine the volume of the actual capsule, which will be dilated by a factor of 9 to the nearest cubic foot. Now notice we're dealing with inches on our scale model, but we want the actual capsule's volume in cubic feet. It's a square base, which is 26 by 26, but if it's dilated by a factor of 9, multiply both those measurements by 9. 26 times 9 will give you 234 inches. And the height was 15 inches, but it will also be multiplied by a factor of 9, and it will be 135 inches. So to get the volume of the actual capsule, it will be 1/3 area of the base, 234 squared, times the height, 135. When you multiply 234 squared times 135 and then divide it by 3, you get 2,464,020 cubic inches. They want the volume to the nearest cubic foot, so by using dimensional analysis or factor label method, we know 1 foot is 12 inches, but we're dealing with this 3 times, so we've got to cube it. When we do, the cubic inches cancel, and when we take and divide 2,464,020 by 12 cubed, we get, approximately rounded to the nearest cubic foot, 1,426 cubic feet. In this lesson, students explore the relationships between the surface areas, volumes, and pyramids of corresponding faces of similar solids.